about to start. We'll talk about code or whatever we'll talk about today. It's about to start, so please hang tight while I check that everything is okay. Sound check, camera check, lights check. How's my hair? Oh, wait, I don't have any hair. Maybe put some pants on and I am good to go. So get ready wherever you are, 'cause this stream is about to start. Get ready wherever you are, 'cause this stream is about to start. Hello everyone and welcome. This is the 2021 and 22 of Advent of Code. Oh no. With me here
And
as
20.
always is David. Hello David.
Hello.
So I saw some messages from David while I was traveling, and he has been pulling his weight, and so have I. So I have a quick win that I can share because I was like, oh no, we are falling behind. Let me do something on the plane while I am traveling. So I pulled up day 21, and I have 1 star for us for day 21. Yay!
Yay. Great.
I did the easy part, but I got a message from my friend, Yappy, who you know, and he said he said this yesterday. This was the first day in which I had to cheat. I looked at other people's answers and I don't understand, and not even cheating, it was easy. It took me a long time and a lot of effort to cheat. So I'm like, oh my god, part 2 of this is going to be a nightmare. And I haven't read part 2. But part 1 was very straightforward. So I just went ahead and implemented that on the plane. And now we can talk about it. So do you want to do day 20 because you have been working on it? Do you want to do day 21? Because you just want to see the star that I got and we can leave part 2 for later? Or do you want to do day 22 because, well, today is day 22?
I would like to discuss day 20.
All right.
But there's two issues. Number one, I don't know where to go with it. I don't really know where to go with it. And secondly, my visualizations are on my machine.
That's all right. Do you want to perhaps... I started sharing my screen with you on Skype. Do you want to share your screen with me?
Is that going to be all right?
Of course, yeah. Press the button.
Okay.
I'll be pressing buttons here on my side to make the screen appear.
All right, sure.
So please bear with us as we press buttons.
Oh no, I need to enable Skype, share screen.
And then you're going to have to restart Skype, right?
No, I think they fixed that in the latest OS. Yeah. Now, I mean, it's very easy to run this. You just do because it's TypeScript, I needed some bundler. But
wait, couldn't you use CSM? I know, because you were running in the browser. Okay.
Yeah, so I wanted to run it in the browser. But it's actually even better than TSM. So now I just wanted to show you I think I will just change this. So we have another input example, which is yet again simpler.
Yeah, and meanwhile, people on the stream are like, what is he talking about? I'm working on it. It's going to show up on the screen in no time. Believe in the process, friends. Believe in the process. There. Isn't technology great? I just made
Ah.
notifications, and now people on the stream can see David's screen.
Brilliant.
Modern technology. You're not going to believe it. Oh, and Nick is here on the chat. Hello.
Hey Nick.
You look a lot better than a few days ago, Nick says. Day 22 is the most fun, but it will take a long time.
Oh man, I think we might. I don't know. We might have to end up completing it after Christmas. We will see how that goes.
And I fixed the double
but
audio
anyway.
that Nick mentioned. It was because I was pressing buttons in some places, but I think the double audio is gone. Thanks for saying that. And you should not hear. Yes.
Cool.
Fixed now. Okay. Yeah. Thanks. Excellent. So the infrastructure here is ready. David, what do you have for us?
So this is basically the realization that you were right to think about counters.
Excellent.
So you, so these gray lines indicate that there's no output here.
Wait a second.
Going in
These
between.
gray lines. All I see is a picture of London.
Oh, am I sharing the wrong screen?
You may be sharing the wrong screen. I don't know.
Well, it doesn't show me that I'm sharing the wrong screen. Switch screen or window. Built-in Retina display. Yeah, I am showing. Okay, I am going to try quitting Skype and coming back.
Yeah, maybe
it
they
is showing.
fixed part of the issue, but not the entire issue. So while David is turning off and on again, Nick is saying, on mobile, daughters have music lessons, so we'll dip in about 20 minutes. Yeah, we can just see the desktop. That's weird, right? That it would not ask you to restart Skype, but it would show just part of the screen. But I guess it makes sense because you actually need a lot of permissions to be able to see from one app what the other app is doing, because it could be a security concern. So I guess it makes sense that macOS is kind of strict about this, but this halfway route is even worse. Now I see just a picture of London. What's that about? Yeah, now you're not sharing screen on Skype now, are you? It doesn't show like you are sharing your screen on Skype. Here's what I'm gonna do. I'm gonna share my screen, which is gonna take over, and then I'm gonna stop sharing, and then you try again. No, give it a try. Give it a try. Share your screen on Skype. I don't see any screen share at all. Should I turn off and on again? I will turn off and on again. See you in a sec. And here I was praising technology, saying how awesome it was. Hello. So, try the screen share. Oh no, David cannot hear us. I made it worse. Ah, okay. Yeah. Things are going off the wall now. Is your camera turned on? Because I don't see your camera either. Do I have to? Famous last words. You don't see me? Now I see you.
I don't see you. Try sharing your screen.
Now I'm sharing my screen.
I can't see your screen.
Oh, that's just great.
Okay, I'm restarting. I'll be back in a sec.
Okay, you're rebooting your computer.
Yeah, it won't take long.
Okay. I'll see you in a sec. Now we can see you here, David. Yeah, but not for long. Oh, well. So, Nick, tell me, you are doing every day. So have you done day 20 and 21 already? And you're saying that we should try Discord for audio and desktop sharing. Yeah, I have used some other apps, including Discord, because I have had guests in the past who were strict about which apps they prefer to use. The problem is that in any other app, it's a bit more troublesome. It's not terribly difficult, but it's a bit more troublesome to bring the video of the person and the video of the screen of the person and all of that into OBS for streaming. And with Skype, if you install the app, if you don't go to web.skype.com, but if you install the Skype app on your computer, there is this amazing setting, which, Nick, I don't think you have guests in your streams, or at least I haven't seen a stream with guests yet. But in case you do have guests in the future, I think you will want to know about this feature, which is really cool, which is on Skype. There is under the settings, and it's under advanced settings. So it's under calling advanced. You can enable this thing called NDI, which is a way for video streams to travel between apps in the same computer or even between apps in different computers. So you can load an NDI source straight in OBS, and that's something that no other chatting app can do that I know of. So hello, David. You are back. Do you see mine? Okay, and your camera is frozen, but we can let that go because we can hear you, you can see us. Let's continue from here. So, okay, you're familiar with NDI stream, so that's a good reason to do. Talking to Nick here, it's a reason to do Skype, which is usually okay. Just tap into the back buffer of the desktop. I don't know what you mean by the back buffer. Yeah. And Nick is saying that I still need to do part 2 for day 20, which we are stuck on as well, and day 21, which we have never started. Was close to solving day 21, but my solution, which is pretty crazy, didn't work for all test cases. Oh, I'm sorry about your case of edge cases. Oh, and I cannot even hear you here on the stream. Isn't that something? Why would that be?
Can you hear me?
I think I need to do something to hear you, which is pressing a bit more buttons here. And there. And now say something.
Hello?
Now everyone can hear you, and we can even see you. It's amazing. All right.
Brilliant.
So, what do you have for us?
What I wanted to say was maybe you could take over driving. I don't want to risk sharing my screen again. I'm happy to share my code. I wanted to visualize, but basically you saw that video which shows the counter functionality of the code, which means that we can serialize those blocks, which are just a chain of flip-flops into a number, more or less. Like we know how many times it's going to run to get that bit. But then what I don't understand is when it's interconnected, when there's like a loop with a conjunction, for example, or if there's a loop with a flip-flop, how does that affect things? It's not all that simple, basically. And I don't have a good theory of how to do that. And we went away and we were like, okay, let's basically find the desired state that we want the graph to be in, and then let's work back from that and work out how long it will take to get there. So the last one is the interesting one, really, because I sent a few which were just
Yeah, and David is talking about my screen, which I didn't want to share all my conversations on WhatsApp, but I will share this part, which I think is the relevant part. So let me come back to the screen stuff. All right. And then this. Okay, so this is the drawing that you want to see, right?
Mm.
And what are we looking at? What is A, B, and C, and so on?
So these all the squares are flip-flops, and then it finishes in a conjunction. And if you can't move that bar at the bottom, but there's a conjunction
Ah,
before it goes to the output, and that conjunction will only turn on or output low when the flip-flop just before it is high. And if you look at the colors of the arrows and the colors of the boxes, the internal state is represented by the color, and also whether it's outputting that is represented by the arrow. So the internal state right at the beginning, they all start as low, but they're all gray because none of them, if you go, you should be right at the beginning, there should be absolutely, is that not at the beginning? Yeah, you might need to, there. Yeah, so here you can see they're all in low, but none of them are outputting anything because...
did you use GraphViz to generate this?
Yes, like a JavaScript port.
There's a
Which is in
JavaScript
WASM.
port? So
Yeah,
cool.
in WASM. In WASM, yeah.
That is amazing.
Yeah, it was remarkably easy to use as well. But yeah, anyway, so I tried writing some graph layout algorithms in the past, and I knew well enough that they are really not trivial to write. So
Well, I think I could manage to draw this layout.
oh, this one, yeah, this one, fine, yeah. But yeah, so all the grays basically mean there's no output, and then as you've seen this video, if you just play it through, this is 1, and then 2, then 3, then 4, then 5.
Yeah, I
6.
saw that when I saw that you sent. When I saw that you sent this, I was like, yes.
Yeah, but then so this makes sense. But then if you were to have a loop here of flip-flops, or if you were to have a conjunction with a loop, which is what you have in the real example, if you click on another video, I don't know how that...
Wait a second. So this is not the real example, and you have renamed the nodes. No, this is an example that you wrote that is just one flip-flop sending to the next.
Yeah, just to see like how if I can see a pattern here. So this is just like a series of flip-flops. This is how it progresses. It will just be counting up in binary.
Okay.
And then if you go to the previous video in WhatsApp, this one.
So now this is the real input that you have.
Yeah.
Okay. It's cool that it fits on one screen. It's not that many nodes. So I suppose that this is going to be the button and this is going to be the broadcaster.
Yeah.
And then
you can see... Yeah, you see these flip-flops. At the bottom, you can see there are like 4 different conjunctions, which all lead into the final output node. Mm-hmm. And they're all off, right?
And what we want is for all of them to be on, because once all of them are on, then the conjunction will be on.
Yeah, exactly. And then it will output low, and then it will complete, yeah.
So what we want is to satisfy this force. So that's great, because we reduced the problem that had to do with doing all of this all at once into 4 sub-problems, each of which is independent. There are no arrows connecting this cluster to that one, or this cluster to that one, or this cluster to that one. So we can split the problem apart.
Mm-hmm.
Oh, wait, I am wrong.
Well, not quite.
Oh, no, I'm not wrong. This one is kind of close to that one, but it's not the same. So
yeah.
Okay, there are 4 clusters, and we have subdivided the problem into 4 subproblems. That's good news.
Mm-hmm. And then you can see on the right you have this chain. You can see that you have these chains, but often there's like, there's a conjunction node which feeds back in, which I don't really understand how to...
But wait a second. We could, given that we can separate the problem in 4 parts, I bet that these guys at the end are going to light up from time to time. And the problem now becomes, when do all of them light up at once? and that's an LCM. So we could reduce it into a problem of 4 numbers or 4 cycles that we need to find, and take the LCM of the 4 cycles. Oh, and if I
That's
take my
a great
cursor
idea.
off, then the overlays go away. That's much better. So, so how does that sound?
That sounds like a great idea. I think I could work on that. That's all I wanted to discuss, really. Let's show me what you've done for 21.
Do you want to take this offline and work on finding these 4 cycles?
Yeah, let's come back to part 2 of day 20 another time, I think.
Okay.
I just wanted to discuss. I think that's good enough. I think like having that, because we're behind on the problems. I'm excited to see what you've done for day 21 and maybe have a stab at day 22.
Yeah, and Nick is saying, yeah, LCM all over again. Yeah,
Yeah, we
also,
knew there was an LCM, but we didn't understand how to.
Yeah, your visualizations really unlock stuff for us, I guess.
Yeah. Also, I have to visualize your graph is slightly different. If you go to, actually, I think I sent it in one of the earlier videos. You can. It might not be 4 of them. Try going if you close it up. It's fine. I'll send it another time.
No. Don't worry. I am doing that as we speak, and I am opening WhatsApp again so that we can look at that. And have you read day 21 at all?
No, not at all.
Okay. So I can give you a short explanation of that. But before we go there, let's look at this. And you're telling me that one of these is my inputs?
Yeah, go to the first video I sent.
I suppose this is it?
No. Yeah, that looks different, doesn't it?
Well, I see 4 clusters, and I see a conjunction in the end. So I think it may be drawn differently, different layout, but it's the same story.
Yeah, exactly. Yeah, cool. Good to confirm then. You've also got 4 different ones.
I also wouldn't be surprised if the shape of the graph is exactly the same. No, if the shape of the graph was exactly the same, our answers would be exactly the same. No.
Yeah.
So probably these 4 shapes differ.
Yeah. Exactly. Cool.
So now I'll close WhatsApp because I want to not risk showing private stuff. And I will skip over the story and go straight to the problem. You have a grid, or what we call a map in this case. We start here, and we may take steps north and east and south and west. And we cannot go over the walls. These hash signs are walls, but we can walk on the dots. And we will take 64 steps. No more, no less than 64 steps, and you must take a step. So you may not stay in the same square. So, for instance, if you take one step, you will get into this configuration. You could have gone north, or you could have gone west. If you take 2 steps, then from these 2 places, you could have gone further up north, or you could have come back. So you could have been here and went south. Or from here, you could have gone east, and then you would end up in the same place. Or you could have gone west.
How did you take 2 steps, like one in both directions?
Well, I'm saying you could have. So when you take a step, where are all the places you could go? You could have gone north, or you could have gone south. Right?
Right. It's just because the S is no longer drawn. I see.
Yeah. And in fact, this S is reachable in 2 different ways. One is going north and then back south, and one is going west and then back east. In both cases, you end up where you started. And then, if you do it 3 times, then maybe this one can go east, so we end up here, but it can also go south, and we end up there, and so on and so forth. Now, the question is, how many places can you get to? So how many little O's will you have in your board after having taken 64 steps? Exactly 64 steps. And of course, the input grid is a bit larger. My input grid, for instance, is this size, which if you look at it in the mini map,
I know
it makes this losange, which is very satisfying. So
That's the first thing I noticed, actually. That's crazy.
yeah, that's called aliasing. It's pretty cool stuff. Comes up in audio often. So my solution to the problem was, can you take a guess? Do you know where I went with this?
Brute force?
Oh, of course I brute force, but not so naively. I also did something else.
Okay, well, regex.
No,
I
I
would,
wish.
I guess, I'll just think. I mean, I would probably just keep track of all the states, possible states, and then like emit all the values. I guess. Because it is kind of, yeah,
I
should work.
I'll give you a hint. What I did to make this feasible, because if you just do it naively, it's probably gonna take too long. I haven't tried. I went straight to the smart solution, and the smart solution is a genius
Hello?
idea that you came up with to solve the. I forget now. But I left a thing running overnight, and then it just came
Hello?
back the next
Can
day
you
and
hear?
said, "I solved it in seconds."
Ah, the recursive one.
Yeah, the day with the dots and the hashes and the question marks, and you had to replace question mark with dots and dashes.
Yeah, yeah, yeah.
You used memoization. So that's what I did. I used memoization. And once you memorize the problem, it goes reasonably fast. It's not instantaneous, but it was a matter of seconds. So yeah, that's what I did. And specifically what I did is I start here, and then I ask, what are all the possible places I could be in 64 steps? Well, I know that the answer to that is a set of locations, and I know that this set of locations is the same as the set of, I can union the set of the answers for these 4 places and 63 steps. So now I have reduced the problem into 63 steps. And I know that the answer, for instance, for this one is 62 steps if I go here and there and so on. And I ask all these recursive questions and I union the results, but I keep that cache on the side. So if it's ever the case that both this guy and that guy ask the same question of, for instance, both this and that will ask the question, how many places can I get to if I take 62 steps starting here? They're both going to ask this question. So that work is reused. And with that, it goes pretty fast.
So what are you caching actually? The entire board?
I am caching. The key is the coordinate that I'm asking the question about and how many steps can I take from there. So in the beginning, it would be the starting position, 64 steps, and then position 1 above and 63 steps and so on. That's the key of the cache. And the value of the cache is the set of all the places I can go to. So the answer to the problem. So I use recursion and I union the results from all the places. It could be with 1 step fewer. So what you can see here is just me finding the starting coordinate with our lovely label on the loop and parsing the board. But really the core of the solution is just this little function, a cache, a little function that will check if you went over the board or if you went on a wall, and then it returns an empty set. Otherwise, make sure you consult the cache. Otherwise, union the results for the recursive questions, and Bob's your uncle.
Interesting that you start at 64 rather than counting up.
The problem with counting up is that if I were to count up, I would need to do it for every possible dot. And then I may be doing extra work because it may be the case that I can never reach this guy with a single step left. So why would I compute it? I better just do it demand-driven.
Okay.
Yeah.
Yeah, nicely done. Nicely
Thanks.
done.
And this took me all of like 10 minutes. I'm not going to lie. This is not a difficult problem. Part 2 is going to be difficult. So do you want to think
Okay.
about part 2?
Yeah.
Okay.
Tell me more.
Let's see. I haven't read this yet. The elf seems confused by your answer until he realizes his mistake. He was reading from a list of his favorite numbers that are both perfect squares and perfect cubes, not his step counter. Okay, the step counter was this number 64 that I talked about. And he was reading from a list of favorite numbers that are perfect squares. That's 8 squared is 64, and perfect cubes. So that is 4 cubed is 64, right? It is. Okay. Cool stuff, Elf. The actual number of steps he needs to get today is exactly this. Okay, I bet that if I just plug this number into my program, it's not going to terminate in reasonable time. But anyway, he also points out that the garden plots and rocks are set up so that the map repeats infinitely in every direction. Oh, fuck. So I don't go, I have to create a copy of this file.
That's for sure.
Because David will want to get this file later and get his star. Then he is now giving us an example that is this one, which is the example input from part 1. And what you're saying is that no longer we have to do the bounds checking. Also, our number of steps is huge. I wonder if there's something specific about this number, like if there is any property of this number that we should know. Like maybe it's a prime or something like that. It's an odd number, comparison. What are the factors of this number?
Did prime factorization.
Okay, it has 3 distinct prime factors, but that's interesting because this number is large and only 3 prime factors. It has 8 divisors, which are these 3 that we have seen and all the inner products of them. Okay. All right. And I also have to now check. When I check the board, I keep it that way.
So change the big number from 64.
Yeah. And when I consult the map, which I do here, for instance, I have
some kind of modulo, I guess.
I have to modulo with, I want to say just the map length, and here I modulo with the map at 0 length. And how do negative numbers deal with modulo? Yeah, that's no good. So what I want is if y is less than 0, then I will do I want to say something like map length minus y.
Yeah, but you still need to do the modulo.
And even this result may be negative.
Not if you add it.
Not if I what?
Add it.
Ah.
Y% map.length.
Ah, you're telling me that if I do like minus 21, then it's gonna wrap back down? Ah. Ah, okay. Now that makes sense to me.
Mm-hmm. Yeah.
So this is gonna give me a negative number, which I use to index into the map length. Good job. And then I'm gonna do something similar.
Yeah.
Just like that. And for the people like out there who are very nerdy about speedruns like me, this to me feels like the parallel universes in Super Mario 64. As it turns out, in Super Mario 64, there is a bug in the source code that does something odd like this, which means that you can get huge amounts of speed and you can go over you can go out of bounds in the map, but because there is some silly thing like this in the source code, you will be put back in bounds. I guess that's not so silly after all. They wanted to make sure that you would not go out of bounds in the map. But what it means is you can use some tricks to accumulate a huge amount of speed, and then you can use this property of you are never going to get out of the map because of these parallel universes, and then you can get to places really, really fast. Anyway, so let's see if what we have makes sense.
In Python, this would just work.
And I think in JavaScript it will just work as well, right?
No, yeah, but we wouldn't need to do the like less than 0 case because you can just index from the back.
Oh, I can just index from the back. This is 2023, people. We finally caught up to those Python people.
Oh, yeah. So, yeah, now you can just revert it to the first part that you had, there.
Good point. Good point. Nice.
I forget about that. Nice.
So, now we are not going out of bounds anymore, and we are checking the map using Modulus. So we instantiated the parallel universes, and we do not want to move. We do not want to modulo X and Y anywhere else because we do want to visit the parallel universes fresh. And yeah, I think that's all there is to it. Let's continue.
Do we?
Huh?
Do we? Why don't we cache them as well?
We must not cache them because this dot is the parallel universe version of this dot, but they need to count separately. They are two different spots we can get to, as far as I understand.
Okay. All right, let's run it.
Well, let's see if there's anything else here. This is just a tiny 3 map by 3 map slice of the inexplicably infinite farm layout. Garden plots and rocks repeat as far as you can see. The elf still starts in the middle of the tile marked S, though every other S is repeated with a normal garden plot, of course. Here are the number of reachable garden plots in this new infinite version of the example map for different number of steps. So let's see if we have... I guess I should just do... No. Let me think. I will create a copy. So this is our goal. Why do I create a copy of the whole thing? I should just create a copy of this. So with it, 6. We get 16, that's right, with 10. We get 50, and that's right, with 5,000.
Is this on the... Oh. Oh.
Well.
That's fine.
Well, you wanted an integer, isn't that an integer?
It might just be syntax. Do you not have to... Maybe you need to do equals or I don't know.
Okay. So with 5,000, it's already... It's spinning. It's making the computer warmer. With this number, which is 26 million, I guess we'll be here for a while. Now, the good news is that the size of the input doesn't matter anymore because we are running an example input and the real input is much larger, but who cares now? All inputs are infinite.
Mm.
However, the step count the elf needs is much larger. Starting from the garden plot marked as on your infinite map, how many garden plots could the elf reach in exactly that number of steps? So, the problem is not so trivial, but it's not terribly difficult too. And even with our huge stack size, we are still failing. In what way are we failing? Oh, I ran out of memory on the computer. I bet that the stream was lagging too. No dropped frames. But anyway, so that's not gonna fly. We cannot instantiate infinite maps. We need to do a simple for loop, David.
Oh yeah. Did Nick solve this one? But he said he's still working on it.
I think he said he's still working on it.
Oh, he could join us then.
Oh, and Shubham is here.
Hi, Shubham.
Hello. So let's see what Nick said. I still need to do part 2 for day 20 and 21, and we are working on part 2 of day 21. Was very close to solving day 21, but my solution, which is pretty crazy, didn't work for all test cases. So, yeah. And I've written a visualizer to do 6 degrees of separation in WPF, which I think is the Windows framework for web stuff, I think. I don't remember. Yeah, and he's saying it's LCMO all over again for day 20.
He's off.
Yeah. Breadth first search with a single scene shared by all. Okay, so it's not terribly complicated because I have an idea of how to go about this.
Okay.
The idea is that when we get... No, this is not the right day. When we get to the edge of the original board and we are about to get into the neighbor board. By the way, is there any... there is something funky about having no walls around the edges, right? Does the real input comply to this?
Yeah, that would be useful. Yeah, it does by the looks of things. That means you should be able to reuse. You shouldn't have to create infinite.
Yeah, so what I'm thinking is, when you are here and you're about to go east, you are about to go over the board and wrap back around to the first position. You could say, I am arriving in a completely new board at this position. And let's say that I still have 1,000,000 steps. So I am for sure I will for sure be able to get out of the board again. Where are all the places that I can get out of, and how many steps will I have left when I get there? Well, among one of these possibilities, it will be I will arrive here with however many steps left. 1,000,000 minus 100. I will arrive here again. And then I can say, okay, so now I can reuse this answer that I have computed before. I know that arriving from here in the board, I will be able to arrive here in the board with 100 steps to spare, or having used 100 steps. So you just reduce this problem of navigating the whole board and exploring all possibilities over and over, doing a bunch of recursive calls. You reduce that into a problem of like essentially a graph. Right? This is a graph in which being here with 1,000 steps is a stage, and then you transition to this other stage, or you transition to itself actually with 100 steps. And because of the fact that the number of steps is part of the stage, this turns into a bit of an awkward situation. So maybe you don't want to simply have a state machine. You also want to have an associated stack, which turns into a context-free language. Isn't that fun?
The context-free language, I don't know where you're going with that. But I guess high level it makes sense. that
Yeah, what I was trying to
each
say
time
that
you-
there is that there is this well-known relationship between languages and automaton. That's part of automata theory. So regular languages correspond to finite state machines. Every finite state machine can be represented as a regular expression, and every regular expression is translated into a finite state machine. That's how most regular expression engines work. They translate your regular expression
yeah.
into a finite state machine and try to traverse the finite state machine, reaching the terminal node. And similarly, every context-free language is an automaton that has a state machine and a stack. But all right, we don't need to get into that. You were going to say
Yeah.
something.
Okay, but it has a finite state machine and a stack. And how does that relate to the problem?
Well, the finite state machine would be, my initial node would be, for instance, I arrived into the board from here. And then the terminal nodes would be every edge of the board. And along the path, you would pay the price of getting there. So you would annotate each edge with the number of steps that it takes to get there. And then when you arrive back here in the end, you will have paid that price along the way. And the stack is like how many steps you have consumed so far. The steps that you have used to get here all the way from the start in the original universe.
But doesn't it matter where you started? Because here where are we starting? We're starting not like you could be entering the new board from a different position than the one you first started counting. And isn't all the positions relative to where you started?
Well, there are two symmetries of the problem that we can reuse. The first symmetry of the problem is what I used on the first part, which is the fact that you can get to the same node with the same number of remaining steps through different paths. And that's the dynamic programming that I did on part 1, the cache, the memoization. And that's symmetry number 1. Symmetry number 2 is the fact that given that you arrive in a board from here, it doesn't matter if you arrived here with 1 million steps or 2 million. You will be able to get out of the board in the same places having used the same number of steps. This is a property of the board. And we can reuse this work, this structure that we uncover. And I'm not saying that this is trivial in any way, but we can uncover this structure of, given the point where I am, how can I get to all the possible exits and how many steps will that have taken? And with that information, we will be able to traverse the boards without doing the whole path. We will just straight jump from one place to the next board.
Yeah.
And then the problem is reduced a lot. But it's not trivial at all.
Yeah, but I see what you mean. Like, in theory, if we just compute everything for one board, we should just be able to, use the same memoization technique and just be like, okay, well, so give me the answer, given that we enter from here onto the board. Yeah.
And it's not even that trivial, because I'm thinking now, I was first thinking of all the cases in which you go out and you explore. You go to different countries, you visit places, you see the world. But there is also the people who will like go to work and come back home every day for the rest of their lives. They will never exit the board. So we also need to think about that case. Yeah.
Well, what if it just stayed in one board, would we even be able to compute that?
If it stayed in one board, we would be able to compute that because we would not do the modulo thing, so memorization would be more effective. We would see even more of the same cases. Also, I think that if it stays in the same board, then we can find how many steps it takes for you to go to work and back home, and then we collapse the problem a whole lot. We just use the same trick that we are about to use on day 20, part 2, which is find the length of the cycle and stuff like that.
Yeah.
All of that is very interesting, and I want to let these ideas simmer because they're complicated ideas. And instead of starting on that, I think we should go to day 22 and try to get 1 star.
Let's do that. Let's do that.
Fact,
I agree.
There is this person who is always on the leaderboards, Johnson something, and I went into YouTube yesterday, and on my front page it was recommending me the stream from that person, and for instance, I guess day 10 that took us like hours to solve, he solved in 5 minutes, that kind of thing. And then I saw that the stream for day 21 was almost 2 hours long, and I was like, oh my god.
Wow. Yeah, it does seem tricky.
And like you said, it may be the case that we finish this after Christmas, and I'm alright with that. I'm here for the fun.
Cool.
Alright, so let's take a look at day 23.
22. I guess in theory I'm driving, although you didn't drive yesterday.
Well, I did, right? I just didn't do it on camera. I did it on a plane, but here we are.
That's true, I suppose. All right, I'll read through it at least. Enough sand has fallen; it can finally filter water for Snow Island. Well, almost. The sand has been falling as large, compacted bricks of sand, piling up to form an impressive stack here near the edge of the island. In order to make use of the sand to filter water, some of the bricks will need to be broken apart, nay, disintegrated, back into freely flowing sand. The stack is tall enough that you will have to be careful about choosing which bricks to disintegrate. If you disintegrate the wrong brick, large portions of the stack could topple, which sounds pretty dangerous. The elves responsible for water filtering operations took a snapshot of the bricks while they were still falling, your puzzle input, which should let you work out which bricks are safe to disintegrate. For example, I have some input here. Each line of text in the snapshot represents the position of a single brick at the time of the snapshot was taken. The position is given as 2 x, y, z's coordinates, one for each end of the brick, separated by the tilde. Each brick is made up of a single straight line of cubes, and the elves were even careful to choose a time for the snapshot that had all of the free-falling bricks at integer positions above the ground. So the whole snapshot is aligned to a 3-dimensional cube grid. A line like 2, 2, 2, 2 means that both ends of the brick are at the same coordinate. In other words, that brick is a single cube.
So the ranges are inclusive. Good to know.
Right. Lines like 0, 10 to 1, 0, 10 or 0, 10 to 0, 1, 10 both represent bricks that are 2 cubes in volume, both oriented horizontally. The first brick extends in the x direction while the second brick extends in the y direction. A line like 0, this represents a 10 cube brick, which is oriented vertically. One end of the brick is the cube located 0, 1, 0, 0, 1, while the other end, okay. When they say ends, do they mean like the top left and the bottom right?
When they say end,
I guess it doesn't. They say like one end and the other end. I guess it doesn't matter, but I guess it's like it could be like the bottom left and the top right, like if you're looking at a rectangle.
I don't think so. I think that it is always a rectangular prism, so it's always going to expand in a single dimension.
Yeah, I'm struggling to explain what I mean, but it's like they're just like opposite points on a rectangular shape.
It's not a rectangular shape. It's more like just a strip, because I don't think that these numbers. Yeah. So for instance, these numbers, you see that two coordinates are always the same. So in this case, it's 1 and 1. So it is only going to expand in one dimension. And in this case, it's 0 and 2. So it's only going to expand in one dimension. And in this case, it's 2 and 3. So it's only going to expand in one dimension. So in every case here, you will see that there are two dimensions that stay the same and one that changes. And that's the direction in which the bricks are growing. So it's not really a rectangle. It's more like a line.
Yeah. Yeah, okay. The ground is at Z0 and is perfectly flat. The lowest Z value a brick can have, therefore, is 1. So 551, 561, 021.
Wait a second, I need to repeat that. Why is the lowest value a brick can have is 1? It should be 0.
Yeah, because ground is 0, so you can't be at ground. You have to be on top of the ground.
Ah, okay.
And are both resting on the ground, but this one was above the ground at the time of the snapshot.
Okay. I can see that.
Because the snapshot was taken while the bricks were still falling, some of the bricks will still be in the air. You'll need to start by figuring out where they will end up. Bricks are magically stabilized, so they never rotate, even in weird situations like where a long horizontal brick is only supported on one end. This is kind of like confetti, then. Is how I'm imagining it. Because they're like 2D shapes, right?
Yeah.
So it can be marked in the diagrams. Okay. At the time of the snapshot, from the side, so the x-axis goes left to right, these bricks are arranged like this. Okay.
So they're giving us like an aerial view. Or no, it's a side view.
Yeah. That's pretty cool.
It is pretty cool.
Rotating the perspective 90 degrees. So the y-axis goes on the left, looks like that. Okay. Once all of the bricks fall downward as far as they can go, the stack looks like this, where question means bricks are hidden behind other bricks at that location.
Okay.
I don't know why. So they're all heading down, right?
Yeah.
At some point, A stops where it is. What's happening on number 2 if we look at the...
The problem here is that they wish they could write multiple letters in each character, and they can't, so they just put question marks there.
Yeah, but what's... Just looking above at the example, I can't remember what it was. So there was B there. So B, why doesn't B hit the ground?
Because
oh, sorry, this is
A is there.
This is so
this is here.
Oh, I see.
Because A is there.
Yeah, so no, but on the 0 x-axis, is it because the shape is contiguous? So like if it hits it on the y or the z or the x, it will stop.
So B cannot go further down because B here, cannot occupy the same space as A there.
Right. Okay. And then C?
Oh, and then what's going to happen to C? Well, C has to stay where it is because it cannot go into B. But E can fall. At least in this dimension it can.
Yeah, E can fall.
And I guess it does.
But it can't. So why don't we see like B and C separately? Like why are they like collapsed?
Well, in
why are they together?
The X dimension here, B and C are on top of each other, but on the Y dimension we actually see that B and C can collapse, and in the Y dimension we see that B and C have collapsed. But then if you look at it from the other dimension, you should be saying B and C at the same time, and you can't, so question mark. Question mark is not I don't know, it's just there are multiples, so I will not tell you which they are.
Yeah, I'm just trying to understand when it can fall and when it can't. Like, I understand that the question mark means that there's two values there, but I'm not really seeing why C was allowed to collapse, but B wasn't able to collapse.
Well, look at it from this perspective. C can go down.
But it can't on the X.
Well, that's because on the x-axis, C here is kind of behind. Remember that this is three-dimensional. We are doing projections. So it is the case that C is above B, but there it's not immediately above B. It is behind and above.
Yeah, I get it.
And in the general case, we shouldn't do this with projections. We should do this with the real views, I guess. The three-dimensional problem, I guess.
This is Tetris. Three-dimensional
Tetris, yes.
Okay. All right. Now that all of the bricks have settled, it becomes easier to tell which bricks are supporting which other bricks. Brick A is the only brick supporting bricks B and C. Brick B is one of two bricks supporting brick D and brick E, and so on. Your first task is to figure out which bricks are safe to disintegrate. A brick can be safely disintegrated if, after removing it, no other bricks would fall further directly downward. Don't actually disintegrate any bricks. Just determine what would happen if, for each brick, only that brick were disintegrated. Bricks can be disintegrated even if they're completely surrounded by other bricks. You can squeeze bricks.
Squeeze between.
You can squeeze between bricks if you need to. In this example, the bricks can be disintegrated as follows. A cannot be, B can be disintegrated. The bricks above it, D and E, would be still supported by brick C. Brick C can be disintegrated. The bricks above it, D and E, would be supported by brick B. Right, and so on. D can be disintegrated, brick above it with F, but still supported by E, and so on and so on. So in this example, there are 5 bricks that can be safely disintegrated, but not, it's like you can choose from 5 bricks. It's not that all 5 can be disintegrated.
Well, all 5 could be disintegrated, yes.
No.
B can be disintegrated and C can be disintegrated. They cannot be both disintegrated, but each could.
Yeah, exactly. You have 5 that you can choose from, but you can't disintegrate all of them, otherwise it would violate some of these rules. Yeah. Cool. Okay, that makes sense. I kind of have no idea where to start with, like, 3D collision detection.
Well, what is the question? Figure how the blocks will settle based on the snapshot. Once they've settled, consider disintegrating a single block. How many bricks could be safely chosen as the one to get disintegrated? And let's look at the puzzle inputs. Okay, it's a non-negligible amount of bricks, and their coordinates are strange. They are all kind of packed in numbers between 0 and 9 on the X and Y axis, and they extend really far up in the Z axis. And I suppose we could use the fact that they are all between 0 and 9 to our advantage here.
How?
Well, we could, and I'm not sure that this is going to be the best strategy, but we could, instead of looking at each brick and trying to detect its collision with every other brick, which is a square problem, an order of n squared, we could look at position 0, 0, and then do an X-ray of all the Z positions. And I'm not sure this is advantageous. I'm just saying it's a possibility.
Oh, yeah, that's smart, though. I like that. You just, like, go all the way up.
Yeah, did you send something on Skype? I heard a ping.
Day 22.
is it really necessary for us to do all the collapsing before we start detecting possibility of the possibility of disintegration?
Say that again.
They are giving in the problem statement.
Do we need to do everything before we...
They are giving us the impression that we need to do this in 2 steps. First, collapse all the blocks as if they have fallen. Then detect which blocks can be disintegrated. I'm wondering whether it's even necessary to do step 1.
Yeah. Can we just work out whether any block is supported by more than one block? Like, I guess what we need to find are singular dependencies. I guess what we need to build is the graph of, like, you know, A to B, and also like C to A, or C to B, and if B is pointed to, supported by, I mean, we could just say it like, you know, B is supported by A and C. A and C. And if we can build this graph, then we can work out anything which has only supported by one. I mean, this is the output format. Just build the output.
I think I see what you mean, but I think of the problem in reverse. Because we are trying to disintegrate the block. So I think it perhaps would be more useful to think like A is supporting B and C. And then we find that Z is supporting B and C. So, hey, we have found
Z is supporting
B
what?
and C. I'm just making up an example. It's not based on the input that we saw. But what I'm saying is, if you find that, hey, this is a subset of that, and it could be even Z could be supporting B, C, and D for that matter. And then we say, hey, this is a subset of that. Therefore, all the work that A is doing, Z has covered. We can disintegrate A. And I think that thinking about it this way is more useful for the disintegration, because we are thinking, I guess, going up while you were thinking going down.
Well, I mean, once we have this graph, it's very easy to compute this graph. And then, I mean, all we have to do is invert. Like
keys become values,
invert,
values become
and then,
keys. Absolutely, yeah.
Yeah, the difficulty is building this. I mean, I think it makes sense to build it this way round.
Okay.
And then it might be simpler for me, instead of doing subsets, to like invert it and then just count them. But either way, how do we build this?
Well, that's the $1 million question, right?
If only it was $1 million.
Well, that's the $0 questions, or not even that, negative dollar questions, because we could be spending this time to make money. But here we are.
Yeah.
All right. So, how about we reduce the problem from 3 dimensions to 2? And then we can think of this as a Cartesian plane. So we could think of like the y-axis, and maybe even I will do Xcoli draw, and you may not be able to draw here easily, but I am just trying to convey a simple idea, so perhaps that's okay. So if we convert this into a 2D problem, then we would have our Cartesian plane here, and then the problem is no longer blocks, it's just like line segments. Like for instance, if we had a situation like this, then there is an overlap between these two. So when this block is falling down, it must stop around here. Why am I saying that 2 dimensions may help us? It's because I think that we may be able to decompose this into 2 two-dimensional problems, and I think that that's why they were explaining things this way. And
Especially as they don't seem to have like depth, right? They're all sort of 2D shapes. Because if they're just 2D shapes, then we can just like choose the x-axis or the y-axis, and then do you see what I mean?
yeah, and I think that it's particularly important that there are no like L pieces.
Yeah. So like, should we verify that the input has is just made of 2D shapes and there are no 3D shapes?
I have done visual inspection and by sampling. I have done some visual inspection by sampling, and therefore I have concluded that this property holds. Let's just use it.
Yeah.
And that's how we do science, people.
Yeah. That's good enough for me.
So can we solve the 2D problem?
Sure. Easy.
First, I would sort by, and I will just for convenience call these the z-axis, even though it's a 2D problem. So this is the 2D problem for z and x.
And that's also why they've kind of reduced it to like those two cross sections, because you should be able to solve it using that.
I hope that they did that for us. Yes, but even if they don't, even if they didn't, I think that solving the 2D problem will be illuminating in finding the solution for the 3D problem.
So I guess I would write one thing in the corner, which is like, let's look at this at y equals 0. And then we do it at y equals 1, and then at y equals 2, and so on. You see what I mean? Like we do the condition. Do you see what I mean? Like the one that we're visualizing is at y equals 0.
Mm-hmm.
And then we do that for all the y's, and then we've done it, I guess. And we can do it at level by level as well.
Interesting. I was thinking of doing it for x and doing it for y and taking the maximum, because if it has been blocked in either the x or the y axis, then it has been blocked. So I was proposing of doing this exercise twice, and you're proposing to do it more.
I think it would work out the same.
Mm.
So since I'm not an Excalibur, I guess I'm thinking for...
Oh, do you want to be?
Yeah, that might be nice. I'm pretty sure it will end up being the same thing. But more elegant, maybe mine is, I'm not fully sure yet. Yeah. So yours will be like for each Z. For each X, I guess.
Do you mean like for to solve this two-dimensional problem, or how we compose the solution of the two-dimensional problem to solve the three-dimensional problem?
Yeah, how we compose the two.
I thought of composing it in this way, like I would just solve zx, then solve zy, and then go from the bottom up. I would sort the z's, and I would go from the bottom up, and I would try to place this key. This piece. I would try to place this piece, and the place in the z-axis that this piece can go at is the maximum between the solutions on the x and y axis.
Something like that. And the way that I was thinking about it was I guess that's the difference. Does that make sense? Very high level, like I don't have the details elaborated. But you're doing one loop and then the other. I think that's how I'm thinking about it.
Ooh, I have an idea that may solve both at the same time, and it's kind of cool.
Let's hear it.
So let's look at it from the top. And Z is coming from the screen pointing at you. So Z is, I guess in mathematics, people represent this idea of pointing at you with this little symbol. Z is pointing at you like that. And this is X, and this is Y.
Yeah.
And we are at the ground level. So Z is equal to 0 for every place here. And I'm now using the fact that the grid is not only finite, but tractable. The grid size is small. So I would keep a matrix of all the top levels at this point. So to begin with, the top level in every box is 0. Now, sort the pieces by their Z coordinate, and we will start to play. I cannot select multiple. Oh, I can.
You should be able to shift.
Yeah, thanks. There, like so. So sort the pieces by their Z coordinate. And when I say Z coordinate, I mean the lowest Z coordinate of the piece. Sort the pieces by that and start placing them one by one. So I have the X and Y coordinates of the piece, and I will place them on the maximum of these positions. So let's say that a piece is like these 3 locations. So I would delete these 3, or maybe turn these zeros into ones. Now there is a piece here. And suppose that another piece comes by and it occupies these 3 positions. And I will try to place it. Oh, to place it, now I have to turn this into, it's going to be the maximum, right? The maximum between 0, 1, and 0. The maximum is 1. So my new piece is going to occupy places 2, 2, and 2. And then another piece falls down, and it falls on these 3 blocks.
Sorry, say that again. Why is it 2?
The maximum between 0 and 1 is 1. And I'm going to place a piece on top of that 1. So now it's occupying place 2.
Yeah.
Like that. And then suppose that another piece falls down and it occupies these 4 positions here. Well, the maximum between 0, 0, 2, and 0 is 2, so it's going to occupy place 3. And then another piece falls down and it occupies, let's say, these 2 positions here. Well, the maximum between 0 and 0 is 0, so here they occupy places 1 and 1, and so on and so forth. Because there are no L
That's
shapes,
brilliant.
there are no crisscrosses in this, and we can simply... I guess even with L shapes, this has a chance of working. And with that, we will do not only we will do the
You can't
compaction,
describe L shapes
the pieces will
with 2
fall,
coordinates.
but also, as we are placing them, we can tell that it's going to connect. For instance, let's backtrack a whole bunch, or maybe let's just do a new piece. I'm going to put a new piece that occupies these 3 places. By the algorithm, it should touch this piece, right? So I will say 3, and 3, and 3. But not only that, I know that as I was placing it, it only touched this piece. So I can already say, as I am building the tower, I can already say, hey, this piece that was here I need to now remember that it is supporting my piece number 3, or this piece over here. And if it was the case that we had this situation here, and I'm placing a piece on top of these 3 here, then I will need to remember that this piece and that one are supporting the new one that I'm putting at 3, 3, 3. And by the end, I will have the stack, but more importantly, I will have the graph that we wanted to build, the graph of what supports what. And then we can do the subsetting thing that I was mentioning before.
This is beautiful. Beautifully done. Okay, so I guess the we have this data structure which looks like that, and each time we place something.
Are we doing code or Excalibur?
Excalibur. I'm just thinking about like what the type will look like, about what we need to store. We need to store the Z, that it will. One thing is that they don't all live on the same Z, right? It's not just order that we need. So every piece is going to have an ID. The Z that they start. Or no, just like they'll finish, right?
Yeah, for this stacking algorithm that I was describing, you only need to know where it finishes.
And then I guess we can also like do we want to have children for each piece when we place it? Because when we place it, we know what we're placing it on top of.
I am thinking about it this way. See if that helps. I'm thinking of having a matrix, an array of arrays, in which each element is the number that I wrote here, so the current Z, and the piece that was put there to make this into a tree. This will be necessary later when we are stacking something on top of it. We want to know what we are stacking on top of. And then
we also need to take into account the height of the piece, though. Are you doing that?
Yeah, the height of the piece in my examples was always 1. But if this piece was, for instance, for a piece to have height, it will only occupy 1 square. But even if it didn't, the point is just like if the piece is 4 blocks tall, then it's not going to go to a number 4. It's going to go to a number 7. And that's so much. It doesn't really matter.
Okay.
But each piece is a list of other pieces that it supports. And also, I suppose there is also an ID and other stuff necessary here. Or maybe we could just use the identity of the object, the reference to the object in JavaScript.
So you want to say each piece has each piece has multiple supports, but I was thinking of it as multiple children.
Well, when I say supports here is like supports.
I was thinking of it as like
pieces on top.
On top rather than underneath.
Yeah. So this is a list of what are all the pieces that this thing is supporting, because that's the matrix. That's the data structure that we want to build in the end to do the subsetting argument that I explained earlier.
Okay, should we say above?
Okay.
So above, I'm not going to do this. Instead, I'll have like do we want the chords? I think. How about that?
Yeah, I think that's nice because the coordinate I think should be outside because we want to index on the coordinate.
And then we need two more data structures. One is the matrix, which we can just call like, I don't know, should we call it matrix? Which is Z piece an array of arrays.
Yeah.
And then the final one is like initial positions, which ID to piece, right? Something like that.
Yeah.
Okay. And then I just, okay, cool. I think I could write this.
I'm certain you can. I have seen you doing much worse. Yeah, I have seen you solving problems that were much more difficult.
Cool. Let's pass the input. Is this parsed correctly?
I don't see any tildes, so I'm betting
No.
on no.
I don't know what the hell it's taking. Oh, it's trying to like split this stuff. Which is quite funny. A, B. So A, what is that? That's the like start and end. Are they always sorted? Would you be able to verify that?
Hey, that is cute. The answer to that is yes. I will check also on my real input.
Well, it's not too bad if we have to sort them anyway.
So they are sorted in the sense that the coordinates on the left are lexicographically smaller than the coordinates on the right. But of course, they're not already sorted in the z-axis. We'll have to do that much work.
Mm-hmm. Yes. So then we have our lines, and then we have our I don't think what we actually want is above. I think I did that wrong. So what we want is, I'm just gonna, for fun, and then I guess position. Let's do,
Beautiful.
and then we should be able to.
Wait, hold on. That's not right. The initial
No,
positions should be 2 positions here, right?
Yeah, so what should we call this? Position is fine. Yeah, cube.
A piece?
It's not a cube. Yeah, we have piece somewhere else in that Excalibur drawer. I guess we'll come to that.
Did I see supported by?
Yeah.
Okay.
And supporting,
Okay.
for that matter. I mean, we could do a position and a length, but anyway. But that's the thing, we're going to get to, like, supported by and stuff like that in a bit. I guess we could mutate the actual piece as well.
Yeah,
I
let's
could,
mutate the actual piece. Let's just slap on an above list of pieces in that thing.
yeah. And what it can start out with is empty.
And you prefer to have this by ID and then map into something else? Because we could just have a reference to the pieces. As we are building pieces, we could already push into the array of the pieces that are below.
Yeah.
And with that, you don't even need the ID. You could just use the reference of the object as your ID.
That's true. We don't need an ID, but do we need to debug this somehow? Will we need that? I guess not. Okay, we'll come to that. We might need it later. We might want it later. So we don't need ID. Not a piece. Cool. And then, yeah, we want to sort it by Z.
And not only that, but they start Zs. So that's cool.
Yes, because start is always sorted as well. Okay, great.
That's lovely. Can we see the results of parsing just to make sure that they make sense?
Yeah. One sec. I will. Can you see my? Oh, sorry. One sec.
I see a terminal.
Cool. And then, what day is this? 22, part 1. All right.
Yeah, that looks right to me.
Great. So then, now what we need to do, we need to initialize our matrix.
Mm-hmm.
What's the, is it?
It's from 0 to 9.
Is that right?
Well, not quite, because we don't want to fill it with zeros. We want to fill it with objects that have a Z field of 0 and also a piece. And we can create a dummy piece to be the floor.
Yeah.
And it really just needs the above field.
Well, yeah, I'm not sure what to do about that. I guess I'll get to that.
That's fair. That's fair. I like the way you wrote this.
And then in here, I guess I just add the floor piece.
Not only that, we also need the Z.
Oh yeah, that's right.
Yeah.
I don't know why it's doing this, like, weird. Okay, this as unknown as piece thing. So what we need is like a type matrix, or just let's do cell for now. Is like, yeah, piece and Z,
Mm-hmm.
and then I did this wrong for sure. Because everything's better when it's one line.
I prefer one line, yeah.
Cool.
And I will slap a type annotation here. This needs to be a cell list.
Nice. Yeah. Great. And now we need to, I guess, place the pieces.
Yeah.
So first we get the max Z,
Yeah.
and we go for something like this. In the Y, I mean, there's only ever going to be one Y, right?
Yeah, but that's all right.
This-
It could extend on the X or on the Y axis, so what you wrote
Right.
is nice. And then
Yeah.
if
What Copilot wrote is nice. And then, yep.
yeah.
This looks nice.
And now we need to find, so let's go over this loop again to find what are the pieces that have the max Z.
Yeah. We kind of want this to be a set, don't we?
That would be nice.
Why didn't I just do new? Yeah, that's nicer. And then
But don't, no, don't. You don't want to do that outside the if.
do we need a separate?
You could do it in one pass if you wish, but every time you're resetting max Z, you need to reset the set as well and then add a piece. Can I write this?
Yeah, I guess this should be greater than or equal. Right.
Yeah, no. Can I write it?
Sure.
Because if you do greater than or equal, you don't want to reset every time. So what you want to do is, if it's greater than, then the existing pieces needs to be reset.
Yeah.
And if the cell Z is equal to the max Z, which now has been reset, then add. This is what it needs to be.
Yeah. Yeah, I was thinking of it greater than or equal.
But the problem
Okay,
with the
yeah,
greater
this
than
one.
or equal is that you would be resetting more often than you need.
Mm-hmm. Yeah. Yeah, you're right. Okay, nice. I like that. Now that we have set the existing pieces, well, actually, we could probably go ahead and, if we made this a set, up here, the above, then actually we could just do this all in line. Actually, no, we kind of need to do it at the end anyway.
No, but I like the idea of the above being a set of pieces, because we will want to do set operations later.
Mm-hmm.
I will go ahead and fix this one as well, okay?
Yeah, thanks.
And
You shouldn't need to type it, actually, because... And also it's...
also I got it wrong.
Yeah. All good. So now we just go through the existing pieces and we add this piece to the above. That makes sense. And then...
No. It's the other way around.
No, because we're adding this piece above the existing piece.
Yes, it's correct. It's correct.
And then we could call it piece to place, but then it becomes very like we're a marketing team. And then we need to place it in the matrix.
Yes. And for that, we need to calculate the height. And there is a line that I've been meaning to write here, and I want to do it now.
Go ahead. Mm-hmm.
And what I love about this line is that it has a +1. Our old friend, an off by 1 mistake.
Oh, yeah. Because they gave it to us where it's inclusive. Yeah. Nice, nice. So then...
I wanted to write this line so I wouldn't forget the +1.
Nice. And we place this piece on that XY with, is this right? That is the height. Is it? Is there a +1 here?
No, there is not. That is right. Yeah.
I'm not so sure, because if it was 0, and we come along and we place a piece of height 1, then its Z will be 1, which is correct. Okay.
Okay.
And now that we have that, this is weird to me. XY.
It doesn't really matter, but I agree with you. Let's do Y and Z.
Yeah. Or Y and X, you mean?
Yeah,
that's why
Y
I feel like
X.
that's why we should have that's why it should be row and column, but we're definitely dealing with Y and X here, so okay. I guess it really doesn't matter here because it's a 10 by 10 grid no matter what.
Yeah.
Okay, so now we've placed the pieces. Should we print the board after each iteration, or should we just check that we got the right?
Oh no, let's not check anything. Let's sketch the next part. Let's do the subsetting thing.
Yeah. So what is the problem statement again? We need to work out which ones can be removed. Which ones can be disintegrated.
Yeah. So that part is super fun to write. Because all we gotta do is say pieces and then filter.
Mm-hmm.
And then we want to filter such that a piece has a subset or equal, so less than or equal, than the set of above from another piece.
Or we do the inversion thing.
No, we don't need to invert. We already built the thing in the rate that we need.
So here we have the things above it. And we want to see the things which are... Well, we do if we want to find out supported by.
But we don't need to know supported by. What we are interested in is what is this piece supporting? Is it supporting a subset or equal of another piece? Because if that is the case, then it can be removed and everything else will stay in place.
The subset thing. Yeah, I see what you mean. Okay, so for each piece, for other piece, can be disintegrated, true. And then if, let's say can be disintegrated, true. And then I don't think we have subset. Do we have subset?
Unfortunately, we will have to write down subset, but if you want, I can do that for you. It's really quick.
Oh, that's okay.
Or maybe there is. Let's find out. Ooh, it's one of those experimental things that I bet is only available in Safari. Oh, what a shame. But congratulations, Safari, for being ahead of the game for once.
Oh yeah, good point. If the if other piece, no, if each of these, what would you call them? Let's just say, if it doesn't have it, then is subset is false. And then, I don't know why this is not working. I don't know what, I mean the types, but I'll get to that. So, yeah. True break. This is really confusing the way I've written it.
Ooh, the problem here is the in.
Of.
Yep.
That's Python.
That's Python. For those of you following at home, in gives you the keys. Off gives you the values. In the case of a set, in doesn't even make sense, does it?
I guess you can iterate through it. The items, I don't know. So we want to work out if it's a subset. If it is a subset, then it can be disintegrated. And we're going to check through each of those. I think this is correct. Could probably be simplified. It feels like we don't need a subset and can be disintegrated, but yeah, what do you think?
I'm gonna buy that, yeah. Continue.
Okay. And then so let's do this for, oh, we need the ID, I guess. Somehow.
Why?
Well, we don't necessarily, but we need a way of like at least verifying it based on the
They start and end are your IDs.
yeah. But like, you know, on the example they have eight as eight or whatever. It's like we could reference it against that.
Mm-hmm.
It's not a word. Disintegrator. Okay.
That is very Ruby on Rails, right?
Yeah. Oh, sorry. Why Ruby on Rails?
Oh, they love making words like this. Like, um, they have an idea of concerns, I think is the name that they call, which is a cross-cutting thing across multiple controllers, and then it's always an adverb. So that you end up with things like log-inable or words that
Yeah.
don't make sense. But anyway, you're getting a count in the end, and that's good news.
And it looks correct for the example.
What? You're telling me you solved just like that?
It looks like we did it. Yeah.
Can we paste in my inputs? Because I want to see that. Is it okay?
We can, of course. Yeah. Paste them in.
Okay. I will wait for you to do the boilerplate for us. Because I will have to leave in 5 minutes, but if we can get 1 star, I'm gonna be ecstatic, because this is not a trivial problem.
No.
Oh, this is...
Not at all. Yeah, paste it in.
All right.
432.
Ah, the answer is too low.
Really? Oh no. All right, where do we go wrong?
And
Is
your answer right, or is it too low as well?
I didn't try. I just assumed it'd be wrong if yours was wrong.
Okay,
Yeah, it's also wrong, and it is too low.
it is too low as well. Okay.
So we are. There are some pieces which can be disintegrated. Do you think we've placed it correctly, or do you think it's the counting which is wrong?
Could it be the subset? I haven't really grasped your subset logic, but I want to make sure that you have subset or equal.
Should we implement subset?
I think you do
Yeah,
have the
so-
right logic, though.
Is subset T for each one of A? If B has it, then return false.
Yeah, but I don't want subset. I want subset or equal. Are you sure that this logic does that?
Yeah, so this checks if basically if A has something which B doesn't.
I see that, yes. So this seems solid. This seems like it's subset or equal.
Yeah.
Do you think that there is a flaw in the strategy, or do you think that there is an implementation detail?
I think there could be an issue with plus ones,
Okay.
but I'm not totally sure. I'm wondering if I could refactor this to make it clearer what's going on. Because I feel like if I get here, then its subset is false, so I can just break. And then if I didn't break, well, I need to break out of this. And I need to break out of that. I guess this is fine. I don't see. I'm sure there is a simpler way.
And also, you are saying that there is an off by one, but you're not going to the code that has the potential of having off by ones, because by this point,
No.
we will have already computed the sets.
Yeah. I'm just looking at this code because that's where I see the light. But
Okay.
you're right. I need to stop following the light and have a look at where I actually think the problem might be. So I think this could be suspect. Like this has the potential for off by ones, even though at the time we checked it and it seemed good. And should we check that?
Yeah, I suppose the next step is going to be something like going. I wanted us to sketch a whole solution, because what if we got it first try, right? But I suppose now we need to go step by step and think with even smaller examples, like what happens if I place two pieces? Are they going to stack correctly? And what if there are like three pieces and two of them are going to be in parallel? Do they stack correctly, and stuff like that?
Do we need yeah. Do we need a better representation of the... Oh, is this an issue?
I don't think so. Because the ranges are inclusive.
They are inclusive. And that's why we needed the +1 here.
Yeah.
Okay. So I think I agree. Let's do what you said. So let's do a very simple input where it's like I think, should we just start by placing this one and see what it looks like? Should we print should we print the matrix?
I guess that's the best we can do, yeah. Which is not
Okay.
super easy to look at. Maybe what we want to print is not the whole matrix, but just the z's, so that it kind of matches our Excalibur drawing.
Yeah, that's nice.
Conveniently done by this piece of code, yes.
By Copilot. Oh.
Whoops. I pressed some buttons by mistake here.
Can you see the console?
No, it's okay. Yes, I can. So,
I mean, they're all zeros, so that's not working.
wait. In the beginning, they are all zeros. That's working. And then you place a piece.
But then I print... Yeah, but I don't see any...
Top-
Oh, there
top
it is.
left, yeah.
Oh yeah, there we go. Sorry, my camera was in the way of seeing that.
Ah.
Cool. Yeah, so that looks right. Is that placed in the right place that we expected? So what was the piece? It looked like 1 0 1 to 1 2 1.
Looks right to me.
So it's actually, I mean, it's going from 1 to 2, isn't it?
It's going from 1 to 2? No, it's going from 0 to 2 on the y-axis.
Mm-hmm. But the height is inclusive, so it's like occupying. It's occupying. It's got a height of 1.
Yeah.
Okay. So then let's place something across it.
Well, let's place the second piece from the example input.
Yeah.
I like that.
Yeah? Is that what we're expecting? Cool.
I like that.
But this has got a height of 3. Shouldn't the Z...
No, the height is 1. It's a Z of 3.
Oh, yeah. Yeah, sorry. Read it wrong.
I like that.
Again, height of 1. I mean, we know we got the right answer for for the example, but even so, okay.
Yeah, but it seems like not only we got the right answer, but we also got a logic that is our implementation is matching our way of thinking about the problem. So maybe there is a problem in the way that we understand the solution here, but yeah, I can see that. Yeah, I like that. And then yeah.
So this goes 0.
Yeah. Falls on top of the other 2 pieces.
Okay. Should we try and think of some edge cases then that we didn't cover?
It went from, let's see, from 4 to 6 because it has a height of 2. Yeah. And besides looking at the matrices, how about we also now look at the above set to see if we are building that right.
Yeah.
Yeah, we don't want to look at it when we are placing it.
You mean after we've placed it?
Ah, okay, this is after we placed it. Okay.
Yeah. Do we not want IDs at this point?
The ID is the start and the end, right?
It is, but it would make it easier to see what's going on here because it has this like nested visualization. You see what I mean?
I see what you mean, yes, but I am just looking at the number of elements in the above set, and that seems correct to me. As we were building up the thing, I kind of remember how the building went, and I think it looks correct to me.
Okay, that's good knowledge. Definitely the last one should have empty.
The last ones have empty, and we had one that had a height of 2, and it was above a single block, and then I remember that it was above a single block, a block that read like 444, and it read 464 later. And I bet that it's this one, the third to last. So yeah, everything seems to be checking out. So maybe there is no problem with our implementation, which is remarkable because you wrote a first sketch and it was right to begin with.
With a little bit of help from our friend.
And maybe the problem is in the technique that we are using. So there may be edge cases that aren't covered by our technique. But I think we need to let this one simmer as well.
Yeah.
And then come back
to
it.
I feel like it's so close, but yes, sounds good. Got to head off. But yeah, great fun.
Yeah, I'm having a good time. These problems are not just like busy work and off by one mistakes. They are like they're juicy.
They are juicy, definitely are.
Yeah, let's see what people have to say and then sign off. So Procrastinator is here. Hello, it's nice to procrastinate with you. And Fotis, hello Fotis. Faisal, hello. I was doing the inverse. I looked for pieces that cannot be disintegrated, those that are only support for some other piece. A bit easier to me than doing subsets.
Yeah, that was my thinking, I think.
So you would look at pieces that are only supported by one piece.
Yeah.
I think I see it now. And yeah, it may have been simpler.
We would just reverse the... We still have to reverse the map, but that's okay.
Or even build the way that it is... don't reverse the map, but do it as you're building it.
Yeah.
Want to know what's wrong? No. Don't spoil it. Strategy. Oh. Did I miss that part? I don't know. Is this a spoiler? I think this may be a spoiler. I'm not reading it. Are the bricks sorted by Z? Yes. What if you mix up the inputs? That's all right. We are sorting it by Z. And what if there are multiple pieces with the same Z? Then they couldn't be overlapping to begin with. So that's all right. Okay, I'm going to read this line. Strategy. You didn't make the things actually drop down, so you can only extrapolate if something is supporting if their Z's are touching. No, we made the things fall down.
Yeah.
So, yeah, there may be some off by ones, but I don't think so. There may be some edge cases, and I think that there are some edge cases in the real input. But all of that and more in a future stream. I'm still not sure when I will be available tomorrow, but it's I will let you know, and then we'll go from there.
Yeah, keep me posted. All good.
All right, so thank you, Ivasler, Nick, Faisal, Procrastinator, Shubham, and all of you who are not here on the chat but are watching this. I appreciate you being here. And most of all, thank you, David. I will see you soon. Enjoy.
See you soon. Bye-bye.
Thank you for watching the stream. You know how great it has been. Or maybe it sucked, and I am glad that you stuck with me. And soon we'll all be back together for some more coding or talking or chilling. The next time I'll be streaming.